So right now you are looking at the physics flipper book. I don't know if anyone's had the opportunity to go into Mr. Cook's office and just see it propped up against the blackboard. But yes, I did see it. I grabbed it and I thought it would be a fun little way to introduce our project. So essentially what our project is we will be having some sort of vessel, which you'll see later on, moving down a ramp. And once it goes down that ramp, it will be on different surfaces. So essentially what I'm trying to say is we're testing the friction on different surfaces, right? Just to see if there's any variability. So here, this provides some background in what friction is. So as we learned in class, and what we see here from the source is you need some sort of motion on a surface. There needs to be direct contact in order for friction to occur, right? And what we'll be measuring in this experiment is kinetic friction, right? When the object is moving. Just to clarify also, we are not accounting for the friction that is occurring on the ramp with that vessel into our calculations. We are only accounting for the friction that is occurring within the flat surface of our different material surfaces. So you'll see later on when we display the Excel portion of this why this was more beneficial or more accurate for our experiment. So after weeks of plotting, Aiden and I finally developed our first prototype for the vessel, and as you can see, we try to make it as stable as possible. It was really wide, so we would have to use 2 tracks put together, and I actually went home that night and I thought to myself, man, I feel like we could do a lot better. So just like any scientist, we devised some new calculations. As you can see, we went through some really big thought process, and this is a very complex equation that we're putting down to derive how we made our new cart, and the finished product was a lot better. So the reason why we did that is because we felt like this would be the most efficient body or vessel that will go down the ramp. Because with the water bottle car, it just didn't seem very aerodynamic enough, or we just felt like it wouldn't necessarily travel a good amount of distance for us to have valid results to measure. So before we start, I think it's just great to understand what our setup was. We used the dynamics track as our incline ramp, and we had that propped against a wooden block. All thankfully provided by Mr. Cook. And if anyone's curious, the ramp angle was 30 degrees, and the actual height from which we were releasing our car was 0.046 meters. It's actually very important in the way we center and drop the car. Otherwise, obviously, we don't get that straight path, which would complicate our calculations. So we are now testing it on the lab table, and just to measure the distance, we were able to get it at 0.184 meters for the first trial, and we repeated it 2 more times, and we got an average, again, of 0.184 meters. So as we were moving the setup and shifting between the different surfaces we wanted to test, it was imperative Aiden and I kept the same height. So now we're just demoing it on a wooden table. Just to clarify, it's more of a smooth waxed wooden table, and the last trial will be on the tile floor.
This is the chillest car on campus.
Cool car.
In the top left of our Excel sheet, we have our original obtained values, including the mass of the cart along with measurements of the ramp. We then measured acceleration, which was key in obtaining our object's final velocity at the bottom of the ramp. This final velocity was calculated to be used as our initial velocity for the main part of our experiment, in the effect of friction on different surfaces. So, for each surface, we inputted the average time and distance of the cart. We then used our time, mass, and initial velocity to find the force of friction opposing the normal force. After that, we divided our force of friction by our normal force to arrive at our long-awaited coefficients of kinetic friction for each surface. And as seen, our highest kinetic friction and force of friction lies within our waxed wood surface, while our lowest is the tile surface. As we can see in these graphs, at a time of 0 seconds on each surface, the kinetic energy for each surface maintains all of the energy as friction from the surfaces have not done any work against. However, in comparison to the carts at 1.5 seconds, we see that conservation of energy across all surfaces vary as the force of friction takes over and converts kinetic energy to internal. For the lab table and the tile floor, we can see that the cart still has a significant amount of kinetic energy, amounting to 60 to 65% of the total energy of the system, while the wooden surface has done an immense amount of work, maintaining only 30% of the kinetic energy being left.
Everybody want to know what I would do if I didn't win. I guess we'll never know.